Welcome to the 18th lecture video for Physics 4C. We continue our introduction to quantum mechanics from last week when we were introduced to the particle properties of electromagnetic waves, or light. In the study of matter, in particular atoms that make up everything, we find that purely classical theories are not able to explain common phenomena. This leads to introduction of additional quantum assumptions, which enable the construction of semi-classical models, which do explain such things as the stability of the hydrogen atom and its emission spectrum. We start with the de Broglie hypothesis, which is an extension of the energy-frequency relationship observed in the photon into a momentum wavelength relationship hypothesized for everything. This relationship is experimentally verified and can be useful in forming our intuition for quantum mechanics. As an introduction for the Bohr model of the hydrogen atom, we start with a historical description of early atomic models, illustrated via a PHYS simulation. To account for the existence of the atomic nucleus, as demonstrated by the Rutherford scattering, while avoiding the catastrophe predicted in the Saturnian model of the atom, Niels Bohr proposed the idea of orbital angular momentum quantization, which leads to the Bohr model, which correctly predicts the spectrum of the hydrogen atom. We wrap up this lecture video by listing the quantum assumptions we have introduced so far. We will see these key assumptions hold true as we introduce the fully wave mechanical formulation of quantum mechanics next week. We do have an extra lecture this week going over some interesting history around the confirmation of Bohr's idea of quantized angular momentum, and some additional mathematical material that will prove useful next week. Okay. So I think that's enough to move on to something new that you have to be told. And that's what's called de Broglie hypothesis. And I don't want to spend too much time on de Broglie hypothesis. I'll just quote-unquote drive the expression. So by the way, I think he's a French physicist. I'm just never going to pronounce. Does anyone here speak French, by the way? No one here does. I keep asking every semester. I don't know how to pronounce it. I say de Broglie because when I try to say de Broglie, I can't really say it right. If someone knows correct pronunciation, teach me. I'm just going to say de Broglie. So de Broglie hypothesis. This he actually got Nobel Prize for his PhD thesis, where he introduced this, which is probably why a lot of physics theorists have a bad habit of introducing unjustified or some whatever. So what this is what sort of a short version of what de Broglie did. He looked at what Planck did, assuming this. He looked at what Einstein did, taking this assumption and applying it even more broadly than Planck himself would have felt comfortable doing. And he looked at it and he thought Einstein didn't go far enough. He thought he should have gone farther. He thought that, so this is a basis of what we call, what your lab manual calls wave particle duality of light. And de Broglie, this is the short, very abbreviated version. He looked at it and he thought, Einstein didn't go far enough. In fact, he didn't have to say of light. He made this assumption, hypothesis, that this wave particle duality exists with everything. For example, if you have this
I was asking, what is the wavelength of this? De Broglie would say that, yes, this does have wavelength. And we can actually assign a wavelength to it. And the way it's experimentally verified at first was, so based on the relationship that he guessed that, you can come up with a wavelength for electrons and protons under certain circumstances. And you can do an interference experiment with these, electrons, protons, and neutrons. And when people did the Young's double slit interference experiment with electrons, they got the result that's consistent with the wavelength predicted by this de Broglie hypothesis. And you can actually get the relationship he was guessing at from here with judicious substitutions, and because this is, I guess, somehow a universally applicable relationship that we just have to do some correct algebraic manipulations and substitutions to get rid of anything that's specific to light. So let's just start out with this. We have energy of electromagnetic wave, or I guess I should really say energy of photon is equal to Planck's constant times frequency of the EM wave. So Planck's constant, we are going to keep it in the end. And as we go through quantum mechanics, you will see this constant as the surefire hint that there's something quantum mechanical going on. So I'd like to rewrite the energy of light into something else so that I can, quote unquote, derive an expression that's more universally applicable than light. How would I do that? Well, energy of light, actually this is the total energy because there's no mass. So you are thinking of this, right? In special relativity, you have this energy momentum relationship. The total energy squared is equal to the rest energy, or the thing that's based on rest energy, plus PC squared. Right? With the light, there's nothing material there that you can slow down and measure. That's rest mass. So with light, you can say that this is 0. And in fact, well, this looks like a valid expression, right? E squared is equal to PC squared, or energy is equal to momentum times C. I'm not dividing anything by 0. I'm not multiplying anything by infinity. Seems fine to me. And this is actually a valid expression. So anything for any particle that's massless, you have this relationship that its total energy is momentum times C. And that's true of light. So this, I can replace it with, all right, energy of photon is the momentum of photon times C. All right, I don't think I really like this C because speed of light kind of seems specific to light or special relativistic circumstances. And I'm hoping that this can apply to something that's non-relativistic, that I can get rid of this C somehow. So on the right-hand side, I see I'm running out of time, so let me just go through this quickly. I see this frequency, which I can rewrite in terms of speed of light. So you have this relationship. The speed of a wave, or speed of light, is equal to wavelength times frequency, right? People remember that? So this, yeah, all right. So frequency, so solving this for frequency is equal to C over lambda. So plugging that in, what you have is H times C divided by wavelength of electromagnetic wave. And once you get this far, then that's where you see that anything that's specific to light wave gets canceled out. So C gets canceled out. And when I was keep asking what is the frequency of this, it's like, what's the phrase? What's the frequency? Can it? Some popular thing, I don't know, whatever. It's hard to say what the frequency could be, or what kind of experiment you do to measure frequency. But if we are talking about wavelength, then there's an experiment you can do to measure it. Young's double slit interference experiment that actually measures wavelength directly. So you have this. momentum of photon is equal to Planck's constant divided by wavelength of the photon. So this is where de Broglie makes the bold jump that it makes. So far he hasn't introduced anything new. What he would now introduce is that he would say, well, we don't need this, that this is a universal expression, that this relationship applies to everything. It applies to light, obviously, and it applies to this ball. So let me just copy it over. He would say momentum is equal to h over the wavelength. This is what we are going to call de Broglie relationship. Because I'm not calling it hypothesis anymore because he turned out to be right. Somebody did this experiment. So, momentum, it's the regular old momentum. If you're doing non-relativistic measurement, then this would be just the mass times velocity. So if you have something that has a mass, and if I throw it up, then it has velocity. Then it has a wavelength. So if let's say I drop it, and let's say it's moving down at 1 meter per second, then I can calculate its wavelength. So wavelength of this thing as it's dropping, and let's say it's moving at 1 meter per second, its wavelength would be, move over here. So it will be h over momentum. It will be Planck's constant divided by momentum, or h over mv. And what do you think that number will turn out to be? Small, large? Small. Yeah, it's actually fantastically small. Let's say this is, I don't know. Let's say it's 10 grams. 10 gram mass moving at something like 1 meter per second. If you plug in the numbers to get what the wavelength is, it's fantastically small. All right, let me just plug in the numbers. H divided by 10 grams times 1 meter per second. I should get something of length, hopefully. Hour, that's not right. Oh. Here's Planck's constant. Okay, so 10 to minus 32 meters. Do people know the scale of small things? What's the smallest thing you know? That's a prefix. But what do you know physical stuff? That's femtometers big. So femto is what, 10 to minus 15? Or 14? Well, so angstrom is 10 to minus 10. Anybody here know what things are of an angstrom in size? Atoms, yeah. Size of an atom is 10 to minus 10 meters. Atomic nucleus is 10 to minus 14 meters. This is much, much smaller than that. And this is actually our explanation of why haven't you noticed this before? Well, for a macroscopic object, it's such a fantastically small number that whatever effects of interference or diffraction you might have tried to measure, you wouldn't have seen it. But the picture changes when you are dealing with the microscopic objects, because then this mass becomes much smaller. When you are dealing with the electron, let's say I have an electron that's moving at 1 meter per second, which is actually super slow for electron. But if I'm now dealing with electrons, electron mass, by the way, it's really hard to get electrons to move that slow. It's a really cool electron if it's moving that slow. It has a wavelength of, wait, what? Electron mass as a unit, maybe. No persistence. All right, 10 to minus 4 meters, or about a millimeter. That's something you can measure macroscopically. And I don't think the experiments did have it. Anyways. So, so once you have microscopic things, that's when you can notice these effects a lot more. That's why sometimes you hear this expression that classical mechanics deals with a low speed. You now know why after we've done special relativity. Low speed macroscopic objects. Special relativity deals with when things are moving fast, speed of light or something close to it. And quantum mechanics, people say it deals with microscopic small things. It's because the quantum mechanical effect, they only become apparent when your momentum is small, which is a lot easier when your mass is small. Yeah. Let me introduce the last of experimental phenomena that people were trying to explain that's leading to all these quantum assumptions. And actually, I guess in terms of quantum assumptions, I have introduced everything that needs to be introduced. So as a reminder, this is where they all came from. This idea that the energy of light waves or electromagnetic radiation comes in discrete packets. This is coming from the black body radiation and photoelectric effect. People have been trying to explain this phenomena on the basis of some basic laws of physics, and the only way to explain this was by introducing this assumption, right? Now, when I introduced this assumption, I kind of put it forward like this was some fun idea that de Broglie was having, and he had no reason to suggest this. That's not, I don't think that's historically correct for one. And there's another thing in the background that was really leading de Broglie to suggest that this relationship might be more general than just the light. That the whole wave-particle duality might not be just a funny property of light. Instead, it might be a more universal phenomenon. And this, so if I'm trying to actually motivate this, this is how we would motivate it. You could call this, if you just want a phrase that you can Google search, you might call this stability of hydrogen atom. And really it doesn't have to be specifically hydrogen atom. It could be really any atom, stability of atom. When you say that, that kind of sounds a little bit funny. What do you guys know about atoms already? I don't think we have talked about atoms yet in this class. Like, what are atoms? No one here knows what an atom is? You've heard of them, right? They talk about this starting in like a middle school. They don't really explain what they are. But if you want to trace back the idea of atom, like where would you say it comes from? Like from your general science education. Chemistry is actually a good place. So the good starting place that starts with the modern physics, you can go all the way back to the Greeks, but I would rather not, is the periodic table, because that's where you have the modern description of an element. The idea that all this different matter is composed of things that don't easily change. Like when I won't do it, but if I hit it somewhere and bend it, the object itself changes, but it's made up of other things that themselves do not change. And chemists have done a bunch of experiments to figure out that there are these different elements. And they've discovered that, for example, pencil lead, which is made out of carbon, has different property than, I don't know, aluminum, which makes up metallic things or whatever. And they've tested the properties. Somebody discovered that the properties of these are periodic. In particular, they were looking at reactivity. How, so hydrogen, well, it reacts with almost anything. So let's skip. Like a lithium, sodium, potassium, and these are kind of later rubidium, cesium, francium. These are all highly reactive material. And when people look at the compounds that lithium, sodium, and potassium form, they tend to form with like fluorine, chlorine, bromine, iodine. So tend to form with these other elements. And for example, like when sodium forms a compound with the chlorine to form sodium chloride, what is that? Yeah, it sounds dangerous, it's not. Well, it can be. So, so that's what the chemists did. So these elements were known since, I keep telling you, physicists are not good historians. I want to say like 1700s, 1800s. That's when they figured out most of this chemistry stuff. Yeah. So this idea of element is scientifically established. You know that they exist. What people didn't know is, so what are these elements like? I mean, are they, so, you know, back in the days of Greece, they had the idea of the 4+1 elements. You know, fire, water, earth, air. Wait, did I forget something? Yeah, fire, water, earth, air, and then ether. That's the classical idea of elements. And when you had those only, you know, 4 or 5 things, it was really easy to kind of imagine what they would be. You say, you know, if something is metallic, then you say it's, you know, it's like made up of earth element in some mixture with the fire element or whatever. When you have, I'm pretty sure they've discovered something close to 100 elements before the days of, well, at least 80 elements or so. Gold, they know, so at least 80 elements or so. When you have this many elements, it becomes harder for you to say that, because this stainless steel, it's made up of really only 2 elements. Well, 2 big ones, carbon and iron. So you need to have a more better idea of, okay, this basic material that's making up our world, we don't have only 5 of them. We are going to have dozens and dozens of them. So we really need to be able to describe these in terms of more fundamental quantities. More, so you need to be able to say, for example, you need to be able to relate how carbon is different from oxygen. In a way, you can say that, well, carbon is made up of, I guess, 6 of something, and oxygen is made up of 8 of something else, something, the same thing. But the way they are different is that carbon has 6 of them, oxygen has 8 of them. So this is where this is the beginning point for the study of atoms, which are really the particles that make up these elements. And the name comes from the old Greek atomic theory, where people thought these, you know, those 5 elements I was talking about, that they could be described by 5 regular polygons. That's how those atoms of those elements are different, and like, whatever. Wrong theory, I won't go deep into it. But in the era of modern physics, we still need to explain what are these atoms made up of. And this is what people were discovering towards the end of the 19th century, getting close to 1800s. So people have discovered, so I guess, let's say, some background material. I guess of the constituents of atom, the first part to be discovered is actually electron. So people discovery of electron by, I'm pretty sure it's by J.J. Thomson, although don't quote me on that because, once again, physicists are terrible historians. But some guy discovered that if you subject atom to some conditions, you can get particles out of it that's not an atom itself. And he measured the properties of the particle that comes out of it. And the electron was discovered in I guess what we could call cathode ray experiments. So cathode ray, everyone here knows what cathodes are? I guess your photoelectric effect like kind of mentioned about cathodes. So this is an electric experiment. As in, so you have some evacuated tube. So inside here, it's a vacuum. And what people were doing was, well, I have some electrode, piece of metal that's poking in here. And don't ask me why they were doing this. They were applying voltage to it. So, you know, imagine hooking up batteries to it. Wait, so if I want this to be cathode, that has to be the negative end. So hook up the batteries. And what they would discover is that if you apply high enough voltage, then you would get a beam of particles coming out of here that you could actually see them if you don't make it this quiet vacuum, but put in a little bit of gas, like on, wait, that's not argon, that's silver. Put in a little bit of argon, then you could actually see these particles. You could collimate them. You could put barriers on it so you get a nice beam, and you could and you can measure their properties. Like by amount of voltage you apply, you could get how much energy do you get, and you can put this device under a magnetic field, and then you would see these beams bend. So so from that you figure out what's the ratio of its mass to charge, that sort of stuff, right? So electron is the first of the parts of the atom to be discovered. That gets people thinking about if these electrons, these particles that are negatively charged from the experiments they've done, if this comes out of an atom, then when you look at an atom, then somehow this atom has electrons inside it. And hydrogen atom is special in that it is the simplest atom. From the experiments they have done, they know it's the lightest atom or lightest element. So if we can come up with a theory that could describe hydrogen atom correctly, then there's a hope of extending that theory to more complicated atoms like helium, lithium, beryllium, boron, carbon, and whatnot. Yeah? So that's why we are looking at specifically stability of the hydrogen atom. So from this discovery of electron and the experiments that they have done, they know that this atom must contain inside electrons somewhere, right? All right. So what else should this atom have? Like just taking a guess from the fact that what you know that electron is charged, negatively charged, and what do you know about atom? Like it's some things that just you can kind of guess at from common sense. Properties of atom, whatever this particle of the element is.
It's neutral overall.
Electrically neutral. I say it's common sense because in your everyday experience, just touching stuff, you know that most things are electrically neutral. If atoms make up everything, and if atoms are not electrically neutral, then you're going to have to come up with an explanation why these macroscopic objects are electrically neutral. It's so much easier if you can say this atom is electrically neutral. All right. So you have this thing, particle of the element, and you know that it contains a negative charge inside it, that you can make it pop out. What else must it have? It must have positive charge in there somewhere. So that's really the question people were trying to settle. So you have this atom which is made up of a positive charge and an negative charge. And it's a question of how could you arrange these charges in a way that that you'd get something that's stable and has some particular finite size to it. So I guess I don't want to spend too much time on theories that turned out to be correct. One of the, so the same guy who discovered the electron, he had the idea of how this atom could be made. This is the idea he had. So by the way, this is known experimentally. This is something that can be determined. People actually knew the size of atom. You can get this size from other experiments dealing with, I don't know, viscosity of air or whatever. People knew that atom had a size of approximately 10 to the minus 10 meters. So that's something already known. So what Thomson suggested was, he suggested this plum pudding model. And I have to tell you that this is a nickname that's invented by people who are against this idea. So I don't think Thomson called it plum pudding. But the way the model is described is, well, so in this atom, it has to have this negative charge in it. And from everything that we can tell, this is a kind of elementary particle. It doesn't have any other things inside it. So let's say this is a particle that can be as small as it's a point particle. So you have a very small point negative particle here. If you wanted to stay stationary in an electrically neutral arrangement, one way to get that to happen is by smearing this positive charge all over this space that the atom is supposed to occupy. So you would have this positive charge smeared essentially this entire size of the atom. So that was the very first model suggested. And this gets ruled out what's called in Rutherford scattering. So once again, I said I don't want to spend too much time on it. You can read about it on your own if you want to, which is why I'm giving you all these names that you can Google search or read the textbook. So this model gets ruled out in Rutherford scattering or Rutherford scattering experiment. And I'll just quickly describe what that experiment did. So Rutherford did this experiment specifically trying to settle this question of the structure of atom. Because around the time when he did this experiment, so this idea was out there, but people are still trying to figure out, is this the correct model, or what else could it be? So the experiment that Rutherford devised was this. How many here are familiar with radioactivity, or the idea that there's something called radioactivity? Yeah, okay, good. So unstable particles like polonium and whatnot, those things that were emitting strange radiations like X-rays that scientists like Madame Curie and other people have studied. And I guess by the time this experiment got done, they had an idea that the result of this radiation was, in some cases, charged particles. And Rutherford was specifically working with alpha radiation, which is radiation of alpha particle, which from the experiments he's done, he knew that this alpha particle has charge of plus 2e, 2 elementary charges, and it had a mass of 4 times mass of the proton or mass of the hydrogen. So so there's some radioactive source that's naturally just emitting these alpha particles, and he's directing this alpha radiation at a target. And the target that, it doesn't have to be this target, but the target that he historically used is a target of gold foil. And really the only reason gold is used is for its material property. It's very ductile, it's malleable, so he could stretch it out to be very thin. And the idea was that within this gold foil, you'd essentially have a kind of single or very thin layer of atoms. So that by looking at how this alpha particle interacts with these gold atoms, he could get an idea of what's the structure of the gold atom. And since gold is here, and since the idea is that all these elements would share similar structure, whatever structure gold atom has, we could infer that similar structure applies all the way down to hydrogen. Yep. So there's a prediction you can actually make based on the plum pudding model. So I probably should have mentioned this before, but okay, I did mention this, that in terms of the ratio of the masses, electron is very light. And people back then could have figured that out from the experiments with the magnetic field. They could have figured out that this is a very light particle. So they could figure out that this has 1 1 over 2000 or about 1 over 1800 of hydrogen mass. And since we are kind of trying to put everything else on the positive side, really when you look at the atom, most of the mass is in the positively charged part of the atom. So when you look at this, in this plum pudding model, essentially what you're saying is the mass is kind of uniformly spread out through this sphere of atom. Which is not that unreasonable of a guess. Now, based on that hypothesis, this is the prediction that Rutherford would make. He could make the prediction that if he fires this alpha particle with a fair amount of energy and momentum, as it's going through this gold foil, if this mass is spread out, it won't really get deflected all that much. Right? So it'll interact electrically with these charges. So maybe as it goes through, it'll get deflected a little bit, but not all that much. Because it's like, you have a piece of tissue paper and you shoot bullets at it. You don't expect the bullet to get deflected all that much because it has so much more momentum and it'll take so much force to deflect its path. Now, this is the result from this experiment that rules out this model, is that he got substantial portion of these getting deflected almost straight back. So not all of it. So as it fires these, some of it will get deflected at a very large angle. And if I memorize my numbers correctly, if we look at the fraction that got deflected straight back, it was something like 1 out of 10,000 that got deflected straight back. And so, which is not a lot. But this is a result that's completely inconsistent with this model. Because this model would say that nothing should ever get deflected that much. Like, if I'm firing bullets at the window, I don't expect any bullet to come back and hit me, because that window is not. Well, actually, I don't know about that window. They're blinds. But now, if we are firing bullets at a wall or something that has substantial mass to actually be able to absorb the momentum and send it back, then you might see this. So I've seen this experimental result. This is the conclusion that Rutherford was led to from this experiment. This is, by the way, all kind of pre-quantum. People are just trying to figure out what is the structure of atom. And this leads to the idea of atomic nucleus. That the idea that atom has a nucleus. So before, this is what this plum pudding model was trying to do. People knew the size of the atom. So, all right, this is the size scale I have. I have some amount of the mass. Let's try to spread it over the size of the atom that I know it must have from my other experiments. But this model is inconsistent with these experimental results. So the alternate theory that's put forward is, well, whatever is deflecting these alpha particles back, it must be very dense. It must have almost all of the mass of the gold in a very small portion, so that when these alpha particles are, imagine gold as kind of this. Like if this is the gold atom, then in this very tiny region of space is all of the mass of the gold atom and all of its charge. So what is the charge? 79 plus 79e. So that if these alpha particles happen to come close to this region of space, then it'll get deflected straight back. But if it happens to pass kind of far away, then it'll get deflected only slightly. So that's the beginning place of the idea of atomic nucleus. So what we are saying now is, all right, so if I have an atom, I know from my other experiment that this atom has size of 10 to minus 10 meters. But if I spread out the mass of the atom across this entire space, then at no part I have enough density of charge and mass to be able to give me this result. So what I'm going to do instead is put it in a very small region of space, put all of, or nearly all of atoms' mass. And I guess as long as I'm putting stuff there, I'd also put the other stuff. So mass and positive charge. And Rutherford, from the experimental results he got, he could actually put a limit to how big this can be. And since we have benefit of the modern physics, what the size of the atomic nucleus is about 10 to minus 14 meters. So about 10,000 times less in diameter than the size of the atom. So, all right. So this explains what Rutherford was seeing. And in Rutherford's experiment, you can kind of ignore the electron because it's so light that if it gets in the way, it'll just get pushed away anyway. But it brings us back to the same question as what we were studying out before. If we are being forced to put all our mass and positive charge in such a small region of space, how are we going to arrange this with electron in such a way that we get the size of the atom? Because we cannot put the electron in the same space also. So how would you arrange this with the negative charge of electron? So that we have a neutral atom that has a diameter of about 10 to minus 10 meters. This is where sometimes physicists, or scientists in general, take inspiration from what they see. Do you see anything in the universe where you have a lot of mass concentrated in a small region of space, but when you look at the object as a whole, it's actually, the object as a whole occupies a bigger space than that high concentrated mass?
Galaxy?
Galaxy is one. Go a little bit smaller than galaxy so that it's easier to visualize. Solar system, right? So solar system is pretty big. So like, from the sun to Earth, it's long enough that it'll take 8 minutes for light to get here, however long that is. But almost all of the mass of the solar system is at the sun. Sun has like 99% of the mass of the solar system or something. Actually, I forget the exact amount. Jupiter has, anyways, sun has almost all the mass. Now, and here's one more property of solar system that is useful here. So the thing about, if you were just trying to say, oh, I'm just going to put the negative charge at this distance from the positive charge, the problem you would have run into is that this will get attracted into the positive charge. Well, solar system is held together by gravity. Earth is constantly attracted to the sun, but it's not falling into the sun. Why not? Because it's in orbit, right? So that's where people get the inspiration. And some people, I guess it's called the Saturnian model, like moons of the Saturn. So that's where people put the idea of, oh, we can put this electron in orbit around the positive charge. So, and at least when you start to think about it, then it's an elegant solution. So, because you have a kind of a semi-stable arrangement of this positive charge with the negative charge, and you can maintain this distance, and you have examples in nature, in fact, in motion of the planet, to see how this might work out, how this might be consistent with the mechanics. But it's when you start to think about this in more detail. So this is going to be a kind of a common theme. So like the whole idea of a structure of atom, that's a question that 200 years ago, people 200 years ago, people didn't even have a way to ask this question. these elements were the best that they could do. And to go into structure of what makes up the elements, that's an unponderable question. But with these discoveries, we are able to actually ask the question, what makes up? So how does this electron make up the atom, which is the particle of the element? And the tantalizing thing is that as you look at this, you have an explanation that you think will fit. But somebody comes along and pokes a hole in this nice, beautiful theory. And let me point out that hole. And it's actually something you have seen before. So it's this thing about dipole radiation, right? I've shown you this simulation before, right? Can I turn this into negative charge? I guess I can't. So, all right, so let me just say this is, well, so this is, if this was negative, it would be like the electron in this orbit here. Well, but right now it's not in orbit. Let me put it in an orbit. I think I have a preset here for putting in a circle. So if I put it in circular orbit, what do I get?
Electromagnetic wave.
I have electromagnetic waves, right? Okay. What does electromagnetic wave have that could be troublesome for me?
It will release energy.
Waves carry away energy. So if you have electromagnetic wave, that means there's energy coming out of here. This electron in orbit, it has some amount of total mechanical energy. That's how it stays in orbit. So from the laws of electricity, so having said all this picture, what should not predict is that as this is going in circle, it should also be emitting electromagnetic wave, which will carry away energy. And people have seen this, well, okay, not back then. People today have seen what happens when things in orbit lose energy, maybe with a friction or whatever, they lose orbit. So over time, this would fall into the nucleus. Okay? So now at this point, the only defense you might have, oh, maybe this whole process takes such a long time that that maybe it decays, but the orbital decay will take millions of years. That's why we haven't seen it. Somebody did the estimate, and I think according to that estimate, the amount of time in which this will happen is around 10 to minus 10 seconds or so. I don't remember the exact number, but it's a fantastically small number. So that's where this name that I'm giving comes from, that this is the question of stability of a hydrogen atom. And sort of like with the black body radiation, it's not really a failure of experiment. Like we don't actually have hydrogen atoms that's imploding all the time around us. That doesn't happen. But the crisis here is of theory. We have something that has been around us for a very long time. And if you're just trying to simply describe it like by characterizing it, then we would have been fine. But this is what I mean by tantalizing. It feels like we have all the pieces to be able to give a very fundamental description of this, except when we try it, it doesn't work. We have this little hole that's giving us unreasonable prediction that's just not going to work. So this is the place where someone had to come along and propose a new idea that together with everything else we know about this setup might actually be able to explain it, might be able to explain why this is stable. So this is the place where someone had to come along and propose a new idea that together with everything else we know about this setup might actually be able to explain it, might be able to explain why this is stable. And I guess we can explain it two different ways. Let me give you the solution to this problem by a guy named Niels Bohr. So he will be making an ad hoc assumption. He'll be telling you something which leads to the correct result. but along the process, he has to make an assumption. To which, like, if you ask him, why did you make this assumption? The only answer he can give you is, well, it gives me the correct result. And actually, speaking of correct result, so, you know, the fact that hydrogen atom is stable, just simply explaining that is easy, right? I mean, so this particular model leads to a absurd prediction, but maybe this is just not the correct model. Maybe the plum pudding model is actually correct. Or maybe some other model, like atom being made up of spheres, hard spheres like this. Maybe that's the correct result. So this is where the science of spectroscopy is actually helpful. That's what this particular simulation that I downloaded would show. It sort of tells you different predictions that different models of atom would result. It's sort of dealing with how this hypothetical atom would interact with the light. And let me show you the spectrum so that you have a background for what I'm talking about. Let me pass out this diffraction grading. How many here have seen atomic spectra? I think I've shown that in this class once, right? Was it with the helium? Do you remember? Okay, let me show you the hydrogen spectrum. So, I guess if you would take one and pass the rest around, while it goes around, let me set up the hydrogen tube here so that you can see what the hydrogen spectrum looks like. And so, you know, it's kind of easy to come up with a theory that says your atom should be stable. That seems like that's not a high bar to clear, because like that's yeah. But what's a more difficult bar to clear is explaining something more quantitative. Not merely the fact that your atoms don't implode, which is an absurd result for a theory to predict in the first place, but you have some experimental phenomenon that you see with atoms that now the goal is to explain why do we see that. So, so this is the hydrogen tube. People have been playing with this for a while. When you turn it on, it produces this light, magenta light. People have seen that for a long time. By the way, I kind of have to, I can't leave this on for a long time. I'm gonna turn it off so that I have a little time to explain what I want you to do. So take this diffraction grading, hold it horizontally right in front of your eye. When I turn this on, look at it directly. You will just see the magenta light. But as you're looking at it directly, look to your left or right. Then you will see the line spectrum that's spread out. Okay, I can turn it on for 30 seconds and then I'll have to turn it off again. So look, so those line spectrum, and everyone sees those line spectrum? What colors do you see?
Red and green.
You see red and green. Do you see blue? Yeah, like a cyan or, I guess what you're calling green is actually probably cyan. And there's a more deeper blue there, right? So, that's the spectrum of a hydrogen. And measuring that is the science of spectroscopy, and people have been measuring that for a very long time. And that leads to a kind of predictions. It leads to the prediction of, well, if an atom has a particular structure, then the atom is going to interact with the light in such a way that it emits those specific wavelengths of light. And when you play with this simulation, you will see that with the plum pudding model, it doesn't interact with any particular wavelength in a preferential way. It's just bouncing, the light particles are just bouncing off of this hard surface. And when you choose the plum pudding model, then this also doesn't really interact selectively with the light. Any light coming in, any oscillation, shakes this electron and scatters. And when you have the solar system model, then it goes kaboom. That's the absurd one. What we are going to look at now is the Bohr model. This is the model that led to the correct prediction of energies, which leads to the correct prediction of energies, which leads to the correct prediction of frequencies, which leads to the correct prediction of the wavelengths that you are seeing. So this is kind of a starting place for the Bohr model. And so I will sketch the model, and then I will point out what the quantum mechanical ad hoc assumption he's making is. So this is the Bohr model of hydrogen. So he actually starts from this solar system model. So you start out with, all right, I'm going to have the atomic nucleus that has all of the positive charge at the very center. This is what we'll end up calling proton. So, all right, you have the proton here. And the electron is going to be in orbit around this proton. So you have electron that's in orbit around the proton. If that's all you have, then you get the same absurd result before. So Bohr has to put in one more assumption on top of this to avoid this result. And this is a strange assumption that he's making, which you can defend it actually two different ways. You can defend it on the basis that it gives you the correct result. You can defend it on the basis that it's equivalent to one other assumption that you have already seen. So let me do it both ways. So let me first start by stating the assumption. So this is Bohr's assumption. Quantum mechanical assumption. And it goes without saying it's an ad hoc assumption. If you asked him for, why do you think that's true? His answer would be, well, it gives me correct prediction. Actually, correct quote-unquote prediction, because it's not really a prediction. It's just reproducing what you already see experimentally. And in fact, this is such a strange idea that there were some physicists, Stern and Gerlach, that set out to test this idea. And what they said to each other was that if Bohr's idea turned out to be correct, they will quit physics. They didn't actually quit physics, but it was strange enough that it's not something that came to people naturally. So this is his assumption. He's saying, all right, this electron, it's in orbit, it has mass, so it has an angular momentum, right? So he said, angular momentum, let me assign a letter, L, of electron comes in discrete quantities. That's the assumption he made. And once you make that assumption, you kind of look at how you can discretize this angular momentum. And this is not the first time somebody said this quantity that we used to treat as continuous can take any value, comes in units of something. I mean, it's right there. So the first time somebody tried to quantize it this way, they used this Planck's constant. Well, Planck did it, and we now call it Planck's constant. So this discretization of angular momentum is done on a similar basis. I'm going to write down an expression which won't really be intuitive, but we'll get to it later. So mathematically, you would say this. This angular momentum, it comes in integer units, so of n. So this is integer. It comes in integer units of this. N times Planck's constant divided by 2 pi. Sorry, there's a 2 pi in there for some reason. So actually, this particular combination of constants happen a lot in quantum mechanics. So kind of like with the gamma in special relativity, we give this a special letter. It's called H bar. Or if you want to spell it out, Mathematica calls this reduced Planck constant. So in terms of this, this is what Bohr assumed, that angular momentum of this electron comes in these discrete quantities, n, h bar. So I guess Bohr was somehow assuming that, so with this model in mind, could you have this angular momentum to be 0? Now, if you are a chemistry major, you might know something from chemistry that, in the s orbital, electron has 0 angular momentum. I want you to forget about that for the time being. In this particular physical model we are building, is n equals 0 a possible possibility? It's not. This is one aspect of Bohr's model that is actually wrong. So Bohr's model is not the correct quantum mechanics. It's a stepping stone to the correct quantum mechanic. So that'll be the one thing about Bohr's model that's not quite right. So what's the smallest number you could have for n? You want to put something in orbit. We said this can only be an integer. 1 is the smallest number it can be, right? If it's 0, it's out of the question. Yeah, so that would be the smallest value n can be. And for the chemistry majors here, we actually retain this notation. In chemistry, this is what you call principal quantum number. And when you look at the periodic table, this is the n. 1, 2, 3, 4, 5, 6, 7. Now, the little part that Bohr got wrong was that you could have n equals 1 and the angular momentum be equal to 0. So we'll get to that, but I want to just show you that this plus what you know in classical mechanics leads to the correct result. So this is really, this is what we want to derive. We want to derive an expression for energies of this electron. So we want to say, when this electron is in one particular orbit with n equals 1, we want to be able to say this has energy E1, right? And we want to say if it's on some different orbit with n equals 2, we want to say it has energy E2. And if it's on an even larger orbit, then you keep going with that. On a larger, it's not drawn to scale, by the way. On this larger orbit with n equals 3, we want to say it has energy E3. And this is really what we, to compare this against this prediction in, quote unquote prediction, in spectroscopy you have seen, this is what we want to be able to say. We want to be able to say the difference between these energy levels. For example, E3 minus E2 gives you, so as electron goes from here and somehow goes down into this lower level, as it's doing that, it's going to emit a photon. It's going to emit photon or light as it's doing that. And we want to say that this difference in the energy levels of the electron is where the energy of the photon, h times frequency of, hydrogen spectrum, comes from. Okay? So the starting place here is that we need to derive an expression for the energy of the electron as a function of this parameter n. So that'll take a little bit of time. We have to review some classical mechanics and go through not that complicated of an algebra. Let me use this picture to label some things. So this is what we are going to do. We have this model of hydrogen. And this is what we call semi-classical model. It's because you can analyze almost everything about this classically using the physics that you already know. It's semi-classical, not classical, because at some point we are going to insert our quantum assumption. At some point we'll do something that makes it non-classical. So that's the nice part. We can do most of it classically, and then at an appropriate place we'll put this in later. So let me use this to label something. So I have a proton here, which is so massive that we'll assume that it doesn't move as the electron moves around. And so what we are going to have is, let's say electron is at this one of the orbits that's out here. This is my electron, and it's moving in some kind of orbit here. All right. So we want to write down an expression for energy of this electron. So we want the total energy of the electron. So mechanical energy, kinetic, and potential energy, right? All right. So kinetic energy. I'm going to make a bold assumption that this is going to be non-relativistic. Make things easier for me. So its kinetic energy will be 1/2 mv squared, right? Where do we get potential energy from?
Electric potential.
Yeah, electric potential energy. So this electron is moving in circle, moving at speed v. It's accelerating towards proton because of electric force. So this is where you have to remember. Do you remember the expression for electric forces? Or the name where you can get that? Yeah, Coulomb's law. And so that's why physics 4b is prerequisite for this class, because you're supposed to know it. But if you have to look up, the most important thing to know is the name, so that you can look it up. You look it up in Coulomb's law. Coulomb's law says that force that's pulling this electron towards the proton, this force is given by, I guess I will use, do I want to use K? I want to plug in numbers in, so let me do it in SI units and say 1/4 pi epsilon naught, product of charges. In this case, the elementary charge times elementary charge. So E squared divided by the distance squared. So whatever this distance is, call it R squared. Now this gives the force, but because this is a conservative force, there's a potential energy that we can associate with this. Do people remember the expression for that potential energy? If not, I will, let's not go through the derivation. This is something you would look up. You can look it up in your physics 4b textbook. So, you look up Coulomb's law, read it down to the part where it talks about electric potential. They do the derivation of electric potential energy. And I guess you can look at it two ways. The electric potential due to a point charge that they would derive, electric potential due to a point charge, is equal to potential, that would be positive. So the amount of charge divided by 4 pi epsilon naught times the distance. Does this look familiar? Yeah. And the potential energy of this electron would be the amount of charge minus E times the potential due to the positive charge at the center. Good? Okay, let me write all that out. So this is the expression for the energy. Total energy is equal to 1/2 mv squared minus the elementary charge in the electron times this Q also should be E for the proton. So minus E squared over 4 pi epsilon naught R. All right. So a lot of the quantities here are constant. This is the mass of the electron. This is the electric constant. This is the elementary charge. Some things are variables or dynamic quantities. Speed and the orbital radius. Now, can this speed and the orbital radius take up any value? We are still in classical mechanics. So in classical mechanics, would you say that this total energy is essentially an expression that is a function of velocity and V and R? Like, could this to be any combination? Like, you could have V equals 0 and R equals whatever. Is that right? That doesn't sound right. Imagine this. I have an electron that is in circular orbit around this charge. Could I have V equal to 0? If it's infinitely far away, but it's at this fixed distance r. At this fixed distance r, could my V be 0? No, because if V were 0, then it would get sucked in. So there's the exactly correct V it can have. So this expression that we have here, it's not actually a function of two variables. It's function of only one variable, really. So I'm going to make an executive, let's see, can I make this choice now? Well, okay, so it's, so we could write this as an energy as a function of V, or energy as a function of R, or energy as a function of whatever. But what we first have to recognize is that this speed and the orbital distance, they are related to each other somehow, if you are going to say it's in circular orbit. So let's first figure out the relationship, because that's going to be an important part of how we can derive this expression for energy. So how would you express that idea mathematically, that this speed has to be somehow related to the orbital radius? Like what laws of physics that you know would you bring in? Something that you maybe learned in physics 4A? What kind of motion is this? Circular motion or uniform circular motion. When you have uniform circular motion, what do you have? This is physics 4A, like a second meter material.
V squared over R.
So what does V squared over R give you?
The centripetal acceleration.
Centripetal acceleration. So whenever you have something that's moving in circle, it is accelerating. We call that acceleration. We call that acceleration centripetal acceleration. And this is what you learned in physics 4A. It's the one formula I have people memorize. This centripetal acceleration is given by V squared over R. And the centripetal acceleration, it comes from centripetal force, but centripetal force is not a new kind of force. It's just a way of saying net force. This is your net force. This provides your centripetal acceleration. So with all of that combined, what you can say is this. You can say, all right, my centripetal acceleration, which from the circular motion kinematics is V squared over R. That has to be consistent with the Newton's second law. So this should be equal to the force divided by mass. So it should be, in terms of magnitude, E squared over 4 pi epsilon naught, R squared times the mass of the electron. Okay? So this is a single equation that contains V and R and nothing else. So this is the thing that will relate your V to R. So for example, so I guess it's, yeah, I keep wanting to, yeah, so let me do it this way. I'm going to solve this for V squared. That's going to let me substitute that in here so that I have energy as a function of orbital distance alone. Okay? So, so move R over. That cancels one of the R's here. So I get V squared is equal to E squared divided by 4 pi epsilon naught R times n. Oh, that was easy. Now, when I plug this in here, you will see something kind of funny and nice. This m cancels out that m. This is the same thing you have here. So it's 1/2 times the same thing as this minus this thing. So when you subtract it, you get a very simple expression, which will be, when you plug this in, what you end up with is minus 1/2 times this. E squared over 4 pi epsilon naught R. Like, do people see that? Yeah, this is actually not an accident. There's something called the virial theorem that says something like this always happens, or on average it happens. But that's a nice result, so I'm going to use that. So what that tells me is, all right, the energy as a function of radius can be given as this. Minus E squared over 8 pi epsilon naught R. Okay? Now, so far, everything has been classical. I didn't introduce anything new that you didn't already know. And here's the place where I want to ask this question. Can this R be anything? I mean, just classically. Yeah, classically, this R can be anything. And that's what you actually see in the solar system. Planets, asteroids, they can be at any orbital distance from the sun. There's no law of gravity that tells you the planets can only be at these orbital distances. So that's where classical physics leaves you. It leaves you with saying this electron can be at any arbitrary distance, and it can have any continuous amount of energy. And this is the place where this quantum mechanical assumption enters. So we are going to assume that this is true. We are going to say that, sorry, let me erase and just rewrite a version of it. We are going to say that in this place that allowed a continuously varying energy, we are going to say, well, this is our requirement. Angular momentum must come in units of h bar, or n times h bar. Well, I don't have any angular momentum here, so I have to do a little bit of rewriting to see what the consequence of this is on this. I guess the starting place is rewriting what angular momentum is in terms of other mechanical quantities. How is angular momentum defined again? Yeah, I omega doesn't sound helpful here, right? What's the other definition? Well, like the actual definition of angular momentum. Do people remember?
Cross product.
Yeah, so L is R cross P, right? P is mv. So this is technically R cross mv. Well, look at this circular motion here. This is the R vector. This is V vector. Are they perpendicular? So their cross product magnitude is just RV. And so direction, here points out here, but I don't really care about the direction. So if you're looking at only the magnitude of this angular momentum, then that magnitude is mvr. mvr. So that's the magnitude of angular momentum. Good. All right. So that's what this requirement means. It means this particular combination of quantities, mass times V times R, can only come in this discrete unit. All right. I guess I need to do a little more algebra. So it's the same algebra we did before. So before we got rid of V here, so that I have energy only in terms of R. So I'm going to do the same thing here. Let's get rid of V so that we have some kind of condition on R. Yes? So I'm still using the same expression here. So what I'm saying is, wait, do I want to? Yeah, I need to get rid of V. So what I'm saying is that, sorry, different color. So here, what I'm saying is V is equal to E divided by square root of 4 pi epsilon naught Rn. So let's say plug that in here, get rid of V, see what that takes us, where that takes us. So I have, so I have m times R times that quantity, E over square root of 4 pi epsilon naught Rm is equal to n h bar. I think I can cancel things out this way. I have mr, square root of mr. So I can say square root of this cancels out that. Okay. Let me solve this for r. So solving it for r gets me this. So I'm going to leave r by itself, move everything else over, and then square them. So r is equal to, or everything else moved over. So it'll be 4 pi epsilon naught n h bar. 4 pi epsilon naught n squared. I'm going to be squaring everything. H bar also squared. Let's see, what else did I have E and the M to move over. So divided by E squared times M. Did I do everything else correctly? Yes. So this is the quantum mechanical piece that we are inserting into everything that we have been doing so far that has been classical. We are saying, all right, this expression for R, this is my quantized orbital radius. This R is a function of n. Everything else here is a constant, right? So what we are saying is, well, only the radius where n is equal to 1, 2, 3, 4, those are the only allowed radius for the electron. That's our quantum mechanical assumption. It's a very strange assumption. Once again, there are a lot of physicists around Bohr's time who thought this was a crazy idea. But, well, once you're exploring what is the consequence of this crazy idea. And, well, so this is one of the consequences. I happen to have energy already expressed in terms of radius r. So let's see what this energy is in terms of all these other things. Where do I have space? I guess I can kind of remember this, so let me just erase and rewrite. So energy, according to all of this, is, let's see. So I want to plug in this Rn, or rather, 1 over Rn, right? So that's what I'm plugging in. So I want to plug in all these constants except for n. So it's E squared m divided by 4 pi epsilon naught, skip n for now, h bar squared. So that's, and then I'll have this n squared, so 1 over n squared. That's 1 over r so far, right? Times, and I'm going to write in all the quantities that's coming from all these constants. So I have minus, let me do that in different colors so that we can track them correctly. I have minus, that's coming from there. And then I'm having, divided by 4 pi epsilon naught, okay. So it's going to be this 4 pi epsilon naught squared. Yeah. I have E squared, so this E taken to power of 4 now, and then divided by 2. So 1/2. Yeah. So this is what it comes down to. We are saying this energy, which we are now going to say is a quantized energy. Energy is a function of n, is this collection of constants times 1 over n squared. So I guess here's another way to put it. We can say that this En is, we can say that it's minus E naught, where E naught is all this collection of constants, divided by n squared. And I happen to have the number E naught memorized. When you plug in all these constants, I will write it down, and then let's just show you the Wolfram alpha. This E naught, it turns out to be a pretty simple, easy to memorize number. So it does come in units of energy, and this E naught is 13.6 electron volts. As long as you memorize in electron volts, it's such a nice round number. Let's just confirm that I remembered it correctly. Wolfram alpha. All right, I have to plug in all those right. So I'm skipping minus for now. elementary charge squared, to the fourth power times that m is electron mass. Electron mass divided by 2 times 4 times pi times electric constant squared times, and that h bar is called the reduced Planck constant. Reduced Planck constant squared. I can actually simplify that a little bit, but I chose not to. Is that everything? Guess that is. Let's type enter and just confirm when the screen comes up that it's the correct full expression. So let's see. E to the fourth power times me divided by 2 4 pi epsilon naught squared h bar squared. All right. There it is. In electron volts, it's a 13.6. Nice. I guess it's not exactly round. Nice round number to memorize. So this is, but this is really the key feature that we are looking for. That is verified by experiment. This energy levels. So going back to this, the energy levels. So these are the allowed orbits. So this would be 1, 2, 3, 4th orbit. This is so the energy that it has at the 4th orbit, and the light that's coming from this hydrogen atom, you would say is coming from when this electron is falling from here to some other level. So if it's going from the 4th orbit to the 2nd orbit, you would say that the energy of the photon, or h times frequency, is coming from this difference in energy, E4 minus E2. And when you work out the numbers for this, you should get that cyan wavelength. So this is the picture you have seen, right? This is the spectrum of a hydrogen atom you have seen. And people have studied this for a long time, and people have studied this spacing of wavelengths for a long time. And there was an even experimental law that said that when you calculate the frequencies, or I guess you can put it this way, that this 1 over wavelength was always, you could kind of write it out this way. That's equal to something called Rydberg constant times the difference in the reciprocal of 2 integers. 1 over m minus 1 over n, or the other way around, I forget. This is some law that a guy named Rydberg figured out. It's, without any underlying theory or kind of theoretical derivation, they figured it out from experiment, sort of like a Planck law. And what we now have is a theoretical explanation for this. Forgot, squared. What we now have is a theoretical explanation for this. This is true because the electron energies in hydrogen goes as 1 over n squared, where this is an integer. So, if you ask Bohr, and, if you meet him and that's the thing you ask, why did you assume this? He would say, well, because I get this, and this is experimentally verified. It's not a very convincing reason, maybe, but it is a reason. And this is a beginning place of quantum mechanics. I can give you one more reason that's maybe slightly more convincing than this, and more memorable than this. There is a relationship between this and this. So let me do a little bit of algebra to show that relationship. So let's see. Let me do the algebra this way. So, well, I have here mvr is equal to nh bar. Let me rewrite it. So mvr is equal to n. Let me rewrite h bar once again. So h bar is actually h over 2 pi right? Let me do a little bit of rearranging so that you can see some of the quantities as something that you recognize. Let me put 2 pi over here, move mv over here. So 2 pi r is equal to n times h over mv, or I guess mv is momentum, right? So h over p. What do you see on the left-hand side? What is this? Circumference, all right? Now, if you happen to be aware of the other crazy assumption that de Broglie was making, what can you say about this ratio, h over momentum? That's the wavelength, right? So you could say, well, the right-hand side is n times the wavelength of the electron. So what Bohr's assumption is equivalent to is saying that as the electron goes in orbit, the wavelength of electron, whatever that means, fits in an integer number into the circumference. Yeah?
So it's like standing wave, right?
It's like a standing wave. So you could say that. So yeah, so I think I actually have an illustration. This simulation has that. Oh, de Broglie, that's the one. Can I? Let's see, let me erase all of this. So I don't know if you can really see this well. Let me turn off some of the lights so that you can see this better. This, I mean, circular standing waves are like, how do you have a mental picture of that? So let me just show it to you this way. Oops. So I think I don't have any way of controlling it. I just have to keep shooting light. Let's see. How do I? Oh, there. So what you have here, so these are illustration of different standing waves. At the lowest energy is where the wavelength is exactly equal to the circumference. At each one of them, you fit one more wavelength. The confusing thing here is the wavelength itself changes too, because with a higher momentum, your wavelength gets shorter. But that's what this is illustrating. That's the one wavelength version. And that's the 1, 2, 3, 4, 5. That was 5. But you see why I'm not drawing it, right? So that's the circular standing wave. And this will be kind of a common feature in quantum mechanics. At some point, you have to make a quantum leap. You have to make a leap of assumption that has no counterpart in your classical intuition. So in trying to explain this hydrogen atom, so these two models are kind of equivalent to each other. If you take Bohr's version, then what you are saying is, for no reason whatsoever other than it gives correct result, I'm going to assume this. And this results in all those different energy levels, quantized orbital distance, and all that. You can take this as a starting point, and then you will end up here. Or more precisely, you would end up here. And if you wanted to justify this somehow, as in, like, why should this be true? One way to say this, oh, this must be true because electron must be in standing wave. If that's what you're saying, then that leads you into de Broglie relationship. Or you can take it the other way. And this other way is actually what I would prefer. You can start out with the de Broglie relationship, which has a different way of justifying it, what I did last week, right? You start out from here and you get rid of all the light-specific quantities. So you can start from here, and then you also once again say, oh, the electron must fit in standing wave pattern. Once you combine this with the standing wave pattern, then you arrive back at this. So those are both ways to say it. let me leave you with this. So what we have been doing so far has been introduction to quantum mechanics. And an aspect of that is that I've been saying some things that were not quite correct. For example, it's not quite correct that this, like you have this state of electron that has angular momentum of h bar. That is not correct, right? So let me point out some things that are actually correct in the full-fledged quantum mechanics. And as long as there's no more revolutions in physics in our life, you won't have to correct. This is correct in full quantum mechanical sense. This is the fully quantum mechanically correct expression for orbital angular momentum. It's true that, you know, I guess, okay, it's the G component of angular momentum. And we'll actually use letter M for this. All right, so this is correct. So one thing that Bohr guessed correctly, that's correct even until now, is that angular momentum is quantized. He was not quite correct about the details of how it's quantized, but one thing that is correct is it is quantized. And oh, I guess both things I wrote down here are correct. That's why I wrote them down. They don't have to be corrected. So this is the beginning of quantum mechanics. It starts out with these sets of assumptions that for now are starting out as kind of ad hoc assumptions, as in the only way we could justify it was, well, gives me correct results, so something must be right about them. And what we are going to do from now on is we are going to approach it more rigorously. We are going to have a starting point, kind of like we had, you know, first and second postulates of special relativity. We are going to have some kind of canonical relationship or some kind of starting place. And then everything else can follow from there. And I will tell you, at the level we will cover in this class, we are going to start out, this will be our starting place for many of the things you will see. This de Broglie relationship is the best starting place for many of the full quantum mechanical treatment you will see. And when necessary, actually we will come back to this too, except that we won't have to qualify it for photon. It's energy of anything. Energy of anything is equal to Planck's constant times frequency of the thing. It's just that, you know, frequency of electron is a little bit hard to, like, what frequency are you talking about? But this is a generally true relationship for anything. It's just that in some context, it's not quite clear what we mean by frequency.
So at this point in our coverage of quantum mechanics, I think it's good to spell out and enumerate what I'm going to be calling quantum assumptions. As I say in a few places, quantum mechanics has pragmatic beginning. So a lot of the development of quantum mechanics kind of has this feel of someone trying to figure out the layout of the room in a completely dark setting just by feeling around. And the beginning of quantum mechanics begins with a few ad hoc assumptions. And what I want to highlight here are some key assumptions that turn out to be lasting, turn out to be incorporated into the later, the fully built out model of quantum mechanics. And the first of those assumptions are introduced by Max Planck. It was introduced as he was trying to develop what we call Planck law that explains the black body radiation spectrum. And he introduced this assumption that the energy of an oscillator can have only discrete quantized values. Let me write it in a slightly different way, which goes a little bit better with the format that Einstein used in his explanation of the photoelectric effect, which is that there's this relationship between energy and frequency of oscillatory phenomena, that the quantized energy of an oscillatory phenomena is proportional to its frequency, and the constant of proportionality, uh, letter H, which we call Planck's constant, it's fundamental that there are several different phenomena where you can really only fully explain it by assuming a quantized discrete amount of energy transferring, and this is the unit of that quantized energy. And Einstein extended this idea of Max Planck's to posit existence of photons, particle of light, that he used to explain photoelectric effect. And I talked about how Einstein actually didn't go far enough. The other key assumption that turns out to hold as we later introduce wave mechanics is de Broglie hypothesis. De Broglie's supposition that this relationship between light wave and photon might hold for everything that has momentum. I'm going to write this in a slightly different way, which would be to relate momentum of something like light or a particle, that it's going to be related to its wavelength by Planck's constant divided by wavelength. So this is the de Broglie hypothesis, and this is a kind of a natural consequence of what Einstein assumed about photon. And the kind of surprising thing is that this turns out to hold for everything. And your textbook talks about wave-particle duality, and and this expression relates to both what we typically associate with the particle property, that is momentum, with the wave property, that is wavelength. And I want to, in this short lecture, I want to introduce us to one more quantum assumption that you're going to see later this week. And this is going to turn out to be fundamentally important in many different areas. And I guess in the context of this class, you will see its role in chapter 8 as we talk about the atomic levels and all that. The place where this assumption gets introduced is in the Bohr's semi-classical model of the hydrogen atom. So let me scroll to the place where Bohr's assumption comes in. And, when we talk about the Bohr model, we do say that it's not fully correct. There are some things that Bohr got wrong. But the one thing that will turn out to be correct to a far greater extent than Bohr might even have guessed is this idea of quantization of angular momentum. So the idea that angular momentum comes in this quantized unit of h bar, reduced to Planck constant, where it's a shorthand that we use for h divided by 2 pi. It saves us a lot of writing by not having to write 2 pi every single time. The idea of quantization of angular momentum, it's going to hold for orbital angular momentum, which is what Bohr was considering in his model of a hydrogen atom. And it's going to hold for other kinds of angular momentum, like the spin angular momentum, that you will see more of in chapter 8 later on. So, so these are what I like to highlight as quantum assumptions, because as we introduce quantum mechanics in a semi-historical fashion, some of the things we introduce are not the things that will ultimately turn out to be fully correct. like the Bohr's model. That's not the fully correct model of the hydrogen atom as we understand it. But these assumptions are the things that, as we will turn out, we won't have to change any of these as you learn quantum mechanics better. We'll be able to retain these, fold these into our mathematics of quantum mechanics. So watch out for them as we continue our study in quantum mechanics and physics in general.